if you're with the Colorado Bankers Association, you're in the wrong room, just to let you know. Hopefully you're not confused about that. Glad to be here. This is a really awesome conference. I'm really glad to be a part of it. Thank you for inviting me here to speak. I'm really excited to speak on this topic today, the multi-threaded asynchronous parallel world of Swift. My name is Dion. A little bit about myself. I've been doing iOS development since 2011 and Swift development since day one, 2014. Obviously, iOS is my biggest focus, but I've done Swift in Mac, Watch, and did a talk actually last week in Toronto on Vapor as well. I'm a freelance developer, so if any of you here are looking for a remote contractor, reach out to me. Run my own company called Bright Digit. I also run 2 podcasts. One is called OK Productive with my co-host Eric Gillespie. We do talk about personal productivity and being self-employed dads. And then I have a podcast for my own company called EmpowerApps.show, where we talk about Apple stuff, development, and running a business, and all the quirks with that. A lot of my blog content I put on my learningswift.brightdigit.com blog, so any development stuff usually ends up going there. I have 5 kids at home. My wife's amazing. She's taking care of them on their second week of school. So I kind of feel like I have a little bit of experience dealing with multiple things at the same time. So I'm hoping that, along with my Swift development experience, is going to be helpful today. But we're going to get into why this stuff is important to know and get into a little history lesson on technology. And then we'll talk about specific cases of where we run into this now. And then we'll talk about the different challenges we typically face when doing any of this kind of development, what APIs Apple has provided in the past, and then we'll talk about promises and futures. No talk this week is complete without touching on Swift UI in some capacity, so we're talking about the combined framework. And then a little bit at the end, we'll talk about async and await. So the question we want to ask is, why is this stuff important? Why is parallelism and concurrency and asynchronous stuff important? I think it's been especially important in the last 15 years. I don't know how many of you how many of you have built computers? Okay, good. So, I remember being an older teenager, and every year the processor speeds that would come out would keep getting faster and faster. But around 2005, they kind of ran into this issue where they can no longer put more transistors onto processors. And so clock speeds have kind of stabilized more or less around the 5 gigahertz. Basically, physics says you can't have too many parts in there, otherwise it gets too hot. So instead, what a lot of manufacturers have done over the last 15 years is they've instead preferred to put more cores, essentially more processing units, into CPUs. So instead, what you'll see is that even on the Apple Watch, for instance, you have 2 cores on an Apple Watch, typically one for low power mode and one that can be used all the time and accessed all the time. And then everything to a iMac Pro or the Mac Pro you're gonna get up there into 28 cores, something ridiculous like that. And what that's really meant is we've had to be able to develop our applications in such a way that the operating system is able to organize those tasks so that they can take advantage of the hardware in an energy efficient manner, but also giving the user a better experience. So let's talk a little bit about a couple of terms that I think a lot of people are confused by. Parallelism and concurrency. What does this exactly mean? So in this example here, I have a blue task and a pink task, and these are different ways they can be organized depending on if it's a single core or double core, 2-core processor. And it kind of shows the differences between concurrency and parallelism. If you look at the concurrent one, we only need one processor or one core in that case. And what essentially the operating system will do is it will break apart the specific operation so that it can schedule it in such a way that it'll start one, pick up another, pick up back to the other one, and go so on and so forth. And so that's kind of what concurrency is. It doesn't necessarily mean that they're being done at the same time in the sense that they're both being operated on, but within a certain time frame, they are both being executed. Now, once we add another core, that's where we can take advantage of parallelism and then have one task run on one core and then another task run on another core. That doesn't necessarily mean that the operating system couldn't do both at the same time, which it has that option to do depending on how it organizes the cache on the processor and how that's done. So what's important here is that we give whatever operating system we're working with, iOS, macOS, watchOS, that ability to organize whatever you want your application to do in such a way that it can schedule it accordingly. So asynchronous, what does that exactly mean? So to break that down is oftentimes there are tasks that are heavy duty that occupy a lot of time. And in that case, it's much more helpful to the operating system to listen into when that operation is completed and then run a certain set of code, as opposed to just sitting there waiting, locking down a whole entire application or the whole entire operating system. So obviously we're talking here network, large disk access, some machine learning stuff, anything involving any sort of communication to another device. You're going to run into situations where having your calls be asynchronous would be helpful. So here we have an example, like I'm going to call a web service. We have this time in the middle where nothing is really happening. We're just waiting and waiting and waiting. And then all of a sudden, the API call completes and we get a response back. Would be much more helpful and probably, in the way we usually typically do URL requests is we take that chunk of time out and allow another task to fill in that spot, whether that could be updating the UI, allowing the user to interact with the application. So speaking of which, let's talk about where we run into this situation right now. So first and foremost on everybody's mind, URL requests, right? So typically, in this case, I'm downloading some lorem ipsum markdown here. Right here, simple example, we give it a URL and we give it a closure on what to do when that data task is completed, and then we do something with either the data or the response or the error in this case. Another one is notification center. So you want to post a notification and listen to when that notification is completed. We could take this URL request thing and take it to another level. And now we post a notification and then we add an observer. Again, we have another closure here where we listen to the notification, print it out. This is a playground example, as you can see. So again, we're not just waiting for the notification to happen. We pass in a method so that it knows, or a closure in this case, so it knows what to do when that notification is been completed. We take this to another level with timers. So with a timer, same situation. We can schedule a timer on a 1 second delay when we receive that notification, and then print out a simple message saying timer has been activated. So we've gone through 3 examples where we are passing in a closure, but there's one other situation that I cannot go without talking about, a situation every beginner iOS developer runs into, and that would be UI updates. In this case, everybody's learned you need to do UI updates on a main thread or main dispatch queue. Otherwise, you end up with really strange behavior. So here's an example where we're running a timer, in this case, on a global queue. And then once that, we know since we're running the timer on the global queue, we need to be able to hop back essentially to the main dispatch queue to update the UI in this case with a new label saying, or new label text saying timer activated. So this is an example, whereas the other ones, we we didn't care what thread or what dispatch queue it was running on. This is more about making sure that we follow the guidelines that Apple requires when it comes to updating the UI. So let's do a little computer science lesson just to make sure we have our terms defined. How does the operating system handle this? So firstly, we have the process, which is just a running instance of an application. So whenever you open an application or run an instance, we have a process. However, it's really threads that give the operating system the control it needs in order to schedule tasks accordingly. The one issue you'll commonly run into is what's called a race condition. In the case of a race condition, you're trying to read and write on two individual threads on one set of data, and oftentimes we run into situations like this, where it works fine at first, but then when we get to about 10, the one thread had already read 9, the other thread had read 9, even though the other one had incremented it previously. And so we end up with these double numbers here. So just to go over this example, we have this like thread sleep just to kind of create a situation like a network or a database access where you need to wait. And then every time we have this global array where we're going to read and then we're going to write the next number, but we're running this on two individual threads. We'll run into a situation where one hasn't caught up with the other, and then we end up with a serious issue here where 10, 10, 11, 11, 12, 12, and so on. So one way that we can get around this or to remedy this situation is by the use of what's called a barrier. Typically, we're talking here like a semaphore or a thread lock of some sort. So GCD, which we'll talk about later, has a semaphore, and then what we've done here is we've turned this read-write operation, and we've put it in between the semaphore wait and the semaphore signal, and essentially turned it into what's kind of called an atomic operation. So it acts as if it was a one operation. In fact, it's a set of operations, but the thread can only do one until the other one has allowed the other thread to do so. So that's an example of a semaphore. Let's talk a little bit more about some other ways Apple has provided us to deal with threads and processes. So before I get into that, just some words of advice. Just because I'm going over this part doesn't mean this is the way to do it, but rather I just want to give some context. I highly, highly recommend whatever is the latest abstraction that Apple provides to you, that's what you should go with. But just for the sake of completion, I just want to go over some other ways that you can really get into the nitty-gritty of this stuff. So only on Mac OS, they do give you an ability to run a process or task. So for instance, here's an example of just running a separate process as opposed to like opening an application. We give a URL or a file path to a command we want to run. It runs the list command on a separate process. We pass in a closure where we just basically close the playground, and then we run the process. Process also allows you to do it synchronously, where you can just wait until the process has exited or has completed. But I think there's a lot of utility to something like this if you're running anything on Mac OS and you specifically just want to run an external command and not necessarily, obviously I wouldn't suggest lists, that's why we have File Manager, but there are situations where you want to run a separate command and being able to access what that command does for the user. The other thing is Apple does provide a thread class. So if you want to, you can have a direct, complete control over actually creating an individual thread. No abstraction whatsoever. I don't recommend this, but I wanted to be able to just show that this can be done. In this case, we can just press a block of code or a closure and create a thread that way, and it'll just run that thread right away. You can also subclass the thread and override the main method. You can, if you really want to go old school, pass in an action and selector. It's really up to you. I don't really recommend doing it this way. I think that as we'll go along, there's better abstractions to do this, and it really gives the operating system more control. Now, out of those abstractions, we can't, probably the one all of us have used is a Grand Central Dispatch. How many of you here used Grand Central Dispatch? Okay, even the ones who probably haven't raised their hand have probably used Grand Central Dispatch. So the biggest tool in that shed is a dispatch queue, right? So a dispatch queue allows you to do multiple things at the same time. So here's an example of two counters going from 1 to 1,000. We have one running on a global queue, one running on the main queue. All we're doing is counting 1 to 1,000. And you can see here how it's printed out. It's not one printed after the other. They're just pretty much interleaved in there. And this is really great. I think dispatch queues and GCD does a lot for you. And hopefully in this talk you'll see there's some alternatives that might even be better. But this works. It's pretty easy to get used to and get started. One situation that I'll run into, for instance, is I have a bunch of network operations that are not dependent on each other, but I want to keep track of when they're all completed. In that case, I recommend something like a dispatch group. So let's say, for instance, I want to download a bunch of files, not dependent on each other. I just want them all downloaded and stored somewhere, and then I want to know when all those downloads are completed. In this case here, we create a dispatch group for 20 files. And then I have an empty array of blank strings. I just go through and I say group enter. And then on a outside queue, background queue in this case, I go through, I download the files. Yeah, I know I'm not doing data task with URL session, but for the simplicity of code here, we're downloading the URL as a string and storing it in our array. And then we say group.leave. And then here, just for debugging sake, we're going to print out index. And what that means is I have access to this group, and then on the group, I can either call .notify or .wait, depending on if I want to do it synchronously or asynchronously, and it'll let me know when all those downloads are completed. If you're ever in that situation, this is really easy to do, and as you can see, it's not going to wait for one download and then do the next one. It can let the operating system download as many files at the same time as it sees fit. We did talk about barriers, so just a little bit more. You can also set barriers within a dispatch queue that you create on your own. So for instance, here we've created a concurrent barrier, and when we add to this array, we then set a flag for barrier. That way, we're ensuring that we're not going to add to the array at the same time. The concurrent flag here on this attribute, though, what that does is, while it'll start your operations in order, if you keep adding asynchronous methods to this, it actually won't wait for the previous one to finish to start the next one. So that's what the concurrent attribute can do. So we've seen that we can also do semaphores, but in this case we can also actually set barriers within our dispatch queue itself, as well as how we run the closures. Now, the next level of abstraction that some of you may have seen is operation queues. Operation queues are even a higher level of abstraction when it comes to parallelism, concurrency, and all that. And I think, well, I'll get into it a little bit, but it's really about being able to add a set of operations or tasks that you want done. So in this case, we have a block operation, so it takes a block. For those of you young enough to know, that's like the closure, basically. But here we're adding an operation to the main operation queue, and then it'll just run right away. But I think the real power of operation queues is its ability to deal with dependencies. So in one case, like let's say I want to count from 1 to 200, but I've got it separated into two separate operations. So in this case here, we have an operation counting from 1 to 100, another operation 101 to 200. As you can see, I'm actually adding this one first, right before I add this one. However, I do add dependencies. So when this is actually run, it'll wait for the dependency. It'll actually sort the operations according to dependencies so that the code will actually run in order. So I think that's really where operation queues are super useful, is when you have a bunch of tasks, you know which task is dependent on which other task, but it'll automatically do that, dealing with dependencies and things like that. However, I think there's some limitations with operation queues that I find a little bit frustrating. One is it's not really built around asynchronous operations. If you have an asynchronous operation, it's really difficult to get it to work around. It feels like you're fitting a square peg in a round hole in a sense. There's some code online that'll basically create an operation queue or a queue or an operation, for asynchronous stuff, but it feels like a hack, quite frankly. I'd almost say an easier way to do it is just take your asynchronous operation and make it synchronous in order for it to work on an operation queue. That's what I found, but that's probably one of the weaknesses. The other being, when it comes to dealing with errors and results, it's not really built with that capability, so you have to build your own capability within an operation in order to really track errors and results when it comes to executing this kind of stuff. So, promises for the future. If you've done JavaScript or C#, you've probably seen promises and futures before. Hundreds of languages have these natively built into the language. And I think they're a really powerful way for being able to do any sort of asynchronous operation. There's no need for callback hell. We've all run into that when it comes to Swift, where we have closure within closure within closure. And it really takes advantage of like the functional programming paradigm of being able to do maps, reduce, flat map, etc. when we're doing conversions from one type to another. So I've heard already a few people talk about SwiftNIO. But SwiftNIO has a really great infrastructure for doing that with their futures. So here's an example of some code where I am setting up a website with a theme, and then I simply return an error when it's completed. So what I want to do is I want to convert the one that takes a closure into something that actually returns a future in this case, or what SwiftNIO calls an event loop future. So in this case, we take the event loop, we make a promise, we just specify what type. And then here there's an execute method on the event loop where we pass in the code that we do. And then here we have our closure. And then right inside there, if it's an error, we call the fail method on the promise. And then if it succeeds, in this case, we want to return a site. So then we set the site. And then outside of that, in the actual method, when we want to return the future, we just call promise.futureResult. And pretty simple to do. When we actually run this, all we have to do is call when completed to grab the actual value when that closure is completed. And also, there's a lot of capabilities when it comes to map and reduce. When you want to convert a future value at some point to another value, you have that ability here. So for instance, we have a map for getting the name of the site. And so here this will return a future string. Flat map, if you have a closure that returns a future, you can then, flat map will flatten that future so that it just returns future string. We could also use flatten to convert an array of futures into a future of an array. And then we can also do tuples if we have a couple operations that we want to run at the same time and then return two different types. So again, map is used for converting a future value into another type. So let's say you want to grab a property of a future value, it'll do that. Flat map is for when you want to run another asynchronous method inside your closure, it'll flatten the future so that it's a single future type. And then flatten will take an array of future and convert it to a future of value array. The problem with SwiftNIO, as you probably saw, was this event loop concept. It's okay, but it's really built around server side, quite frankly. If you're doing like an HTTP request or you're handling a database or anything like that, it makes sense because you always have access to that. And there's hundreds of other libraries out there that are trying to basically fill the gap that lacks in Swift when it comes to promises and futures. The one that I specifically want to look at is Google Futures. They do a few things, I think, that are pretty interesting. So let's go back, look at our setup site again, and this time we're going to use Google Promises and Google Futures to pull the setup the site. So in this case, we don't have to deal with an event loop, but rather they expect a dispatch queue, which is something we all know and are familiar with. And then we instantiate the promise generic of site, and it gives us two callbacks, success and failure, and then depending on the result of our setup site, we either call the failure method or we call the success method. That's it. Pretty easy to do. And then when we want to actually execute it, we have here a future that's a result, and then we either call fulfill or reject to catch whatever the error is or if the operation succeeded. This is probably one that I'm more familiar with back in 100 years ago when I used to do JavaScript, but it seems like this makes a lot of sense. I like SwiftNIO's way of doing it, but like I said, I think it's very server heavy, and I almost wish that they'd make the promises stuff a little bit more like what Google does here. Again, you have that ability to convert values using functional programming. So they use a then instead of map for converting values. So in this case, we'll get back a promise string, In this case, we don't even need to care if a closure is going to return a promise or if it's asynchronous or not. It'll automatically do that flattening for us. You can see that here. We can just call it then. They have one method for arrays and tuples. So it'll automatically look to see if it's going to return all the same type, and it'll automatically return an array. And then if it's different types, it'll return a tuple. And we can just use this all method here to do that, to flatten the promises. So I really like Google Promises. That seems to be the one with the most backing, and it seems to be the most useful when it comes to that kind of stuff. Unless you're already doing server-side stuff, I'd recommend that as far as a library. So now we're going to get into the fun stuff with Combine. So let's combine it all together and talk about how Combine fits into all this. So Combine is really concerned more with a subscriber-publisher model in this case, as opposed to the promises and futures. And I think each have their place within the paradigm. We're talking, of course, about reactive programming. This has been around a lot longer than Combine has, especially with like reactive Swift, reactive Cocoa, etc. And it really is useful in the case of anything that's user interface driven. So if you're doing Swift UI, but also I would even say UI kit, app kit, Combine makes a lot of sense in those cases. And it's all built around the idea of subscribers and publishers. Now we had gone earlier over URL requests, notification object, and timer. And what's nice is by importing the Combine framework, they have extension methods to instantiate publishers instead of being required to pass in closures. So here's an example of a view in Swift UI. Hopefully this is like super simple. I try to keep it as simple as possible when it comes to Swift UI. We have this the flag here for observed object, some sort of content object with a name. And what we're going to do is we're going to download that markdown file and grab whatever the header is and assume that's the name of the markdown file in that case. So we need to create this content object. It has to be some sort of observable object. We have a publisher, which has been erased using type erasure. And it's going to return a string. We have a cancelable that we instantiate down here. We have our name property. We just need to say object will send whenever that's changed. We have some method, which we'll get into, called markdown title publisher, which returns our publisher the title of the markdown file or top header. And then here we create the publisher using the method I'm going to show in the next slide. With that publisher, we have to receive on the main thread. Like I said, all UI updates are on the main thread. And then we say what key to assign the value to. And then SwiftUI then does all the plumbing of having to make sure that that's constantly updated whenever that file is downloaded. So let's get into how we create the publisher. So if we go up here, we notice we're calling a method now called DataTaskPublisher. Before we had DataTask, right? That took in a URL and a closure. In this case, we don't even need the closure. We just can do some functional programming in order to handle that. R is basically the data and URL response tuple. So we just need the data. We convert that to a string. And then we grab the first line from that markdown file, which will be the H1 or 1 header. If we don't get that, we throw an error. And then we return the value of that first line. Again, we do a catch. So another layer of functional programming here. This catch will deal with both this error here, but also the download error that may occur with the data task publisher. We want it to be nil, and then we do a compact map to get rid of the nil. And then we erase to any publisher, and now we have an any publisher. And this makes a lot of sense when it comes to when you're dealing with like a stream of values of any kind or multiple values that are going to be coming in constantly. If you're dealing with multiple subscribers, so let's say multiple things want to listen to this object, and SwiftUI obviously tries to deal with that, tries to deal with observable objects. This makes a lot of sense. And I think anything that's user interface focused, the publisher and subscriber model makes complete sense. It's reactive focused, but of course the biggest limitation is I hope you're not going to put this in the App Store next week because nobody's going to be able to run it right away. It only works on the latest OSs, so iOS 13, Catalina, watchOS 6. NTVOS 13. So that would be the biggest limitation, in my opinion, when it comes to combine. And that's something definitely to factor in. So then the question becomes, what's the future of this stuff, right? Well, Chris Latner has a proposal about coroutines, which is essentially abstracting promises and futures even further with what's called syntactic sugar. So just as in Swift 2, we didn't have to deal with this like NS error pointer. I don't know if any of you remember that back in the old days. But before we had error handling, we had that. Well, in a lot of ways, I consider it kind of like that, to where instead of constantly dealing with future and promises objects, we use the syntactic sugar of having the statement have an async or an await in order to both declare and call asynchronous methods. It's a little bit difficult to wrap your head around, but once you get into it, it makes complete sense. The idea being is that if something is asynchronous, everything within that function will also need to be asynchronous. And I think this is easier to read for most programmers in the long run, and it also gives a lot of that control to the operating system that we had mentioned previously. So before I close out, just want to cover some key points. Take advantage of your hardware. Organize your functions, your operations in such a way that the operating system really can take advantage of that and organize those operations in such a way. If they're independent from each other, then organize them in such a fashion. However, avoid convoluted logic in favor of easier maintenance. Make sure that some other developer is going to be able to understand what the heck is going on. Don't try to make it so complicated and so fast that it's going to be too difficult to maintain. And I would say provide a fast UI experience over speed your logic. So in other words, don't just optimize it so that it completely locks down the laptop or it completely locks down the application to where the user, it's not responsive to the user anymore. But rather, it should be responsive to the user first and foremost, and then making it faster as far as execution is concerned. Use abstractions as much as possible, unless you're really an expert when it comes to running individual processes and threads. I think Apple has provided these abstractions for us because in the long run, they're going to be the ones who are going to change the code behind the scenes, and you don't want to be stuck trying to run old discrete methods, concrete ways of creating threads, as opposed to doing it Apple's way, and then if they update things, at least you're still on track. Avoid callback hell whenever possible with promises of futures. And then I think Combine definitely has a future. I would even put Combine more important than SwiftUI in a lot of ways, because I think that underlining plumbing is super important and a great way to organize your user interface and organize your operations in such a way for your device. So if you want to know more, I'm going to be working on a blog post on this. I can send it to you at that. If you go to that URL, I'll send you the blog post when it's ready. Thank you so much. We have time for questions, right? Cool. Questions? Comments? Yeah.
Yeah, so I heard there is actually a very typical that after model, they first added this instead of coroutines.
Yeah, I looked into that too. So there's the idea of the actor, and what it comes down to is it's trying to get around dealing with race conditions, who has ownership over specific data within a specific routine, more or less. I think that's on there. Thing is, I tried to look that up doing this presentation, and I found that article instead. But I know that is another concern that they're looking into, is the idea of actors and ownership of data within a thread. And I even think this async and await stuff, it's going to be a few years down the road before we're going to see it, quite frankly. Any other questions? Sounds good?